speaking about non-workability problems. Thank you.
So, thank you, Boyan. Thank you for the invitation, this nice conference. It's a pleasure to be here. I think second time in IMPA, but in Rio many times because I work here with Boyan. So what I'm going to talk about today is a priori bounds and existing results for some no-local elliptic problems. I will start with what type of operator I'm considering. It's like the fractional Laplacian, but perturbed by a measure of function, let's say. Which it's still the operator will be elliptic. This means it's bounded by above and below by some constant. And what the main requirement will be that at 0, it's the fractional Laplacian. So it's just at 0. Or maybe a constant there. It's continuous, and the limit exists at 0. It's 1, let's say. Just to fix. A constant could be. So that's the type of operator I will considering. So I'm interested in studying existence for no linear equation like this. I mean, the operator equal to a power perturbed by a lower order term with P subcritical, in the sense that this is the critical exponent when you consider the fractional operator. So that's the first model I will considering. And here is I start with it right with the theorem, which says a smooth domain, then for any S, with the K satisfying the assumption I mentioned, if it's really G is a lower order perturbation in that sense, then there exists a viscosity solution. That's the first main theorem, let's say. And the second theorem, it's the same kind of problem, but perturbed with a drift term here, which is a term with a gradient, let's say. And the same type of model, but here we require an extra condition. I want to tell you why this extra condition is needed. I mean, P should be less than n over n minus 2s. We expect that the same result for existence holds if I put the other exponent I mentioned before, I mean this exponent, but we don't know how to prove it, and I will tell you why this problem appears somehow with the gradient. And the theorem is if I perturb, I mean the H satisfies some assumption that in the U part is subcritical and T has some upper bound which is related with the scaling of the equation, then you have a solution. That's the two main theorems I want to talk about today. So what are the tools? The method is topological tools. That means we will use Le-Raychauder degree. And the key point is to prove a priori bounds by the classical scaling method by Gidas and Sprague. I mentioned some names related with no local equation with a drift term. There is Barnes, Chinsei, Imbert, Chen-Veron, Chan-Lara, Davila, and so on. A second remark that I want to mention is that there is a result by Rosso-Odon and Serra, which says that if you have really the fractional Laplacian equation, let's say f is bounded, and u is 0 in omega complement, the solution U behaves like this power. So it's really Holder, let's say, with exponent S. And the problem to consider a gradient term is that the solution becomes, the gradient becomes singular at the boundary. So the gradient blows up at the boundary. You can prove it, really. So to deal with the equation, you have some problem. You need to work with some white spaces to fix, I mean, the problem. So a whited spaces with a distance to the boundary, and to avoid this singularity somehow. So what's the key point? Yes, I will mention there are many tools to establish the result. But the first basic tool is having what they call the Uville type theorem. And if you have a solution of that and P is subcritical, then V is identically 0. This result is already known by Chen Liu, and then there are other which less regular, because this was with some regularity, and then they can avoid this type of regularity for the solution. So you have a Uville type theorem in all Rn, which is some key point when you make the scaling argument. And the other result is by myself with a student, Chia, is what about Uville type theorem in the half space? You need also the Uville type theorem in the half space. And if you consider a solution of that problem with double V 0 in all the half space, the other half space, you have the equation in the half space, you have the boundary condition in all complement, then with P less than this critical exponent, which corresponded to the critical exponent in a one dimension less, then double V is 0.
Are you assuming that the functions are positive?
I will prove existence of positive solution. And all results are with positive solution. I didn't mention, but all this talk is concerned with positive solution.
Considering some finite energy also?
No, without energy, just viscosity solution. Yeah. So the idea somehow there are many works related with existence of fractional equation with variational tools, but here we want to consider really topological truth. So it's another approach somehow of the existing literature. There are many. I don't mention all that kind of work because there are many related to existing results for variational problems. Here I consider not variation somehow problems. That's the point. We observe that this exponent, of course, is less than the critical one, so it's better. Just some words about the proof of that. It's like Dancer's proof, which is we prove monotonicity in the xn direction of that problem. Let's say xn is the direction in the upper plane. And we prove monotonicity using the moving planes method, already mentioned by Isao. So you can really perform a moving planes for that equation and prove monotonicity, and then you take the limit in the xn direction, and then you find the same equation but in one dimension and less. And so if you have the same equation in one dimension and less, you apply the other result that I mentioned before, the Uville type in all space. Just a comment. What you need somehow to make the moving plane work is that you need a sort of ABP estimate in a strip with a small size, which can be obtained. But I don't want to enter into the Uville type theorem because I want to really talk about the existence. So I keep going. So another result we mentioned we need it's the following, which is a GIDAS type result. I want to mention this with more generality. What's the GIDAS type result? It's that the Uville type theorem holds for super solution of an equation like this. Think about that this is the fractional Laplacian. Here you can obtain really a more general thing. What is this dimension here and so on? It's just a fundamental solution. What's a fundamental solution? A fundamental solution, let's take an operator, let's say elliptic operator for the S, and then a fundamental solution means a function that makes the operator, a radial function that makes the operator 0. So the right power that makes the operator 0, and then you can prove, if you assume that the dimension of the operator is less than 2s, bigger than 2s, then you get that if p is less than this critical exponent, you don't have solution. All solution of all positive solutions are trivial. So in particular, you can obtain this result for the dimension for the fractional Laplacian. It's n, so you get this result. And the result is optimal for super solution. Because there exists if p is bigger than this number. So this is the GIDAS type result that we will need somehow, and that's what the restriction come into the assumption. With the gradient term, we need to use really super solution things. I will explain you why. That's one of the. And now we also need some regularity somehow to pass to the limit through Arcella-Scully. So we need some C alpha regularity, and this is even more general, have been proved by Caffarelli Silvestre, the year 2009. Here, as I meant, a more general operator. So you have regularity, interior regularity. So that's one main tool. And the other, for the gradient, actually, there is a work by Kivensov, which says that you really have interior C1 regularity for such type of operator with this type of kernel, because here we don't assume some assumption on the kernel outside 0, so you have C1 estimate. In this work already they have done regularity, C1 regularity, but for not that general kernels, some restriction of the kernel are imposed, but here there is some extension of that. So we have regularities, interior C1 beta regularity. And now I want to talk about a little about, maybe it's not the right space, but the norm I will consider is with the distance with the power here. So the solution somehow where I will make the degree argument and everything will have this, could be holder, let's say, at the boundary, but also the gradient. So it's with a distance to power theta. I will define these two norms just to have it in mind that I need to consider, because what I mentioned before, the solution behaves like the distance to the S. So I need to cancel this. So this will be the norm I will use. So the first thing that I want to mention, that I can control this norm if I take theta to be in between S and 2S. What does it mean? If I have a solution with this bounded norm, then I can control the solution by order 2S minus here, theta minus 2S. And also I have a maximum principle for that equation. So I really want to solve this problem with a singular F right-hand side, singular in that sense because it can blow up in order distance to the theta, to the minus theta. So I have this estimate on the solution. So this is a regularity estimate on the solution. But here the difference that I wanted to f to be singular. That's the point. And how we can prove this lemma and what is related is the following. It's if I compute actually the distance, somehow the distance of a fractional, I will put just the fractional. I mean, if I compute the distance to the power s minus 2s minus theta, then I can really say that this is a constant of this number. I will call it tau. Let's say tau. I will put f of tau. And this is t minus theta. Yeah? So this is a function of tau times d to the theta. In other words, the operator subtract to s to the distance. That's the point. And what about this constant? Because I have this constant just in s and 2s. So, and here I have some uniform control of the mu around and just in a neighborhood of the boundary. But this is the key point of proving the other theorem, the existent theorem, and also the bounds I mentioned. So what's the key point here? It's somehow, to proving this, is also a rescaling argument and reducing the distance to a 1D thing. So that's the proof scaling argument in one dimension. So I put C. Yeah, C I put, because I changed the notation, I don't know, I put C here. What's C of tau? It's the one-dimensional thing. So when you compute it for the fractional Laplacian, it's the distance to a one-dimensional thing. So this is the operator, and this is the constant I get. Maybe here it's a minus Laplacian with the notation I have there. So the thing is, what's the sign of that? I need the sign of this when I define this function, which is the constant there. It's just, I mean, what happened actually when you compute is what I'm doing is the following. It's like xn or x 1D thing to the beta second. That's the thing when you are talking about the second order operator. So this is just beta minus 1, x beta minus 2. That's the 1D thing. Yes, and here I'm doing exactly the same, but well, for a no-local operator where it's more hard to compute the things. But this is the thing is that this function is convex. So, I mean, if you put minus, it's concave. Because I put minus here, then it's concave. So the function is like this, of course. And here's the 1. So the same property has this function. So this function C here has the same property as this function here. Yes, I will call up some. I will just say that in this I will assume tau to be positive. You can compute this for negative value. I don't want to enter into that, but this is related to explosive solution, and you can also compute that. So you can prove that this function f, I can put f because I changed notation. So there was a mistake here, so it's f now, because everything is with f here. So it's just down a mistake there. But what you can prove that this function is say infinity, and if you derive once or twice or whatever, you get a log here because you are I'm deriving this with respect to tau. as seen as a function of tau, and you can see that it's infinity, and you make a, and this integral is not, it's not singular, because if you compute this, you have that it's behaved like t2 squared, so this is integrable. And moreover, this is a concave function, because you get this, when if k is 2 in the before formula, you get that this is negative, so really have a convex function. And moreover, f of 0 is 0, and f of s, I mean, f of 0 is 0, and f of s is 0. So more or less, what you get is more or less, you get this. Here, actually, in 2s is singular, so you get that the function is like this. And here, the value is s. This is a computation that there are many ways to do this. I mean, I know 3 ways to compute this computation. The value at s is really 0. That you can prove it. There are different proof of that, so you can really prove that s is 0, and then you can prove this. And what the lemma says is that this value in between 0 and s is positive. That's the lemma at the end. At the end, the lemma is this, and this gives this regularity issue. If you plug it in, I mean, this is all the work somehow on that. You need to make a rescaling to blow up the boundary and see more the thing in one-dimensional, but at the end, the proof is 1D. But this is the proof, more or less. Actually, you can combine this with the regularity result I mentioned before, and then you can also have an estimate with the theta in there and f in that space, with the exponent plus here, minus for the gradient. So you can improve that. So it's another regularity issue, but now for the gradient, once you have compute this. So these are the starting points. And now I will define somehow the rescaling, because I want to use somehow the same lemma, but for a scale domain. I need the same lemma holds true if I rescale, because the Gidas-Sprague scaling argument has this. You need to rescale the domains, but you define the distance, which is the rescale distance, and with that, I can improve. Even if the domain is moving, you can do the same proof. And then, with comparison with the distance, you can already bound the solution of the equation by the infinity norm with the distance to this power. So if a solution verifies this, of course, you only need this, and then you compare, and then by comparison, somehow, if you have this, you can do this. But here is the difference with respect to the other lemma I mentioned before. It's just that here you need to move the domain, because this is somehow needed when you are making the Gidas-Sprague argument. So the first theorem, actually, I don't want to enter into the existence. I mean, existence is more or less direct when you already have the a priori bounds. So the key point is prove the a priori bounds. Actually, in this setting, when you don't have a gradient term, this is more easy somehow. And when you have gradient term, it's more involved. I will explain. So what you have is that you have a priori bounds of the solution of the first equation I mentioned. Maybe I will put the two equations, because otherwise, I mean, the first equation was something like moving operator minus s u equal u to the p plus g of u x, and the other was the same this is in omega and in omega complement. And the other this is the equation, and P, well, I moved back, so sorry. So this is the equation I mentioned where I have a priori bounds, the equation I mentioned at the beginning, 1 and 2. And of course, G needs to satisfy that it's lower order perturbation. And the other equation is here replacing this by H, which depend on U, X, and the gradient. So I want to give the ideas of the proof. Right? This, I think, is more direct. So you are really, as in Gidas-Sprague scaling argument, and you use the Util-type theorem I mentioned for the fractional Laplacian. And the only point here, I need the thing, the lemma I mentioned. Why I need the lemma I mentioned is just to have the boundary condition on the limited equation. Remember the Util, I will put it like this, the Util-type theorem in the half space let's say complement, was with this condition, and to have U here. So to have this condition somehow in the boundary when the blowing up argument goes to the boundary, to have that it really satisfies this and you don't have problem, you need the barrier. But I will make more details in the case of the gradient, so maybe I will skip it now. But this is just for people that don't know somehow what's the Gidas-Sprague argument. It's just you assume you have a sequence so that the maximum goes to infinity. You pick up the point where the maximum is achieved, and then you rescale your solution with the maximum, so this mu k goes to 0, and then you rescale the domains, and then you see that your solution satisfies this equation, which h of k, a lower order perturbation. But here you see that the rescaling, here at the limit I get the fractional Laplacian because this mu k goes to 0, so I only see at the limit the fractional Laplacian. What's the behavior at 0? And this is a lower order term, so h goes to 0. I can pass to the limit, but I have two situations somehow. One is when this the distance to the boundary times mu to the -1 goes to infinity or to some constant, then maybe I arise with two possibilities. One is in the half space in this case, when this is, and the other is strictly positive. Actually, I can prove that this is strictly positive in any case. So in this case, I have the Util type, the limit of this equation converge to something, and then to this equation or to the equation in the old space, and then I get a contradiction because P is subcritical, and then I use the Util type theorem to get the contradiction. That's the standard thing. So that's the first proof, which is very direct, and now I want to go into the gradient term, which I think it's more involved. So I didn't mention, but here for the gradient term, it was in the theorem, but when consider the gradient equation, I need to assume S bigger than 1/2. I didn't mention, but this is an assumption that is needed. The thing is that the drift term, I don't know what happened. The question is what happened if it's really 1/2, but here somehow the diffusion is dominating. So I will assume S is bigger than 1/2. So what's the space where the singular space, I mean, singular space with the distance, what I will use in all this will be the space E sigma, what I call with this, which is positive there, it's bounded. This is the space. And here I have a restriction. T I can assume it's between 2s. I mentioned the range, but I want to not enter into what's this. But I take a sigma, which is this. This is the factor I need to have the right rescaling. So, but and what's what here is the assumption I mentioned. So if P, remember, is just P is less than the assumption for the gradient will be P less than n over n minus 2s. That's the assumption. So with that assumption, which is 6, and s bigger than 2, and a regular domain, I have a priori bounds in that domain with this norm. So that's the key point, and then with that, I can prove the existence theorem just by degree theorem, as I mentioned before. So how I can prove this? That's somehow the main thing I want to talk. It's how to prove this. So the claim is somehow what they call, it's very similar to a work by Polacek, Quidner, and Supplé, which is, this is the type argument I needed, which is what they call a universal bound on the solution with a decay with the distance. So if I have a solution of my problem, then I have these two decays. So somehow, this in particular tells you that in the interior, with the rescaling half, this tells you that in the interior, the solution is bounded. So the only possibility somehow it's that the point when I make a rescaling argument, it goes to the boundary. But
do an assumption, just to remember, the assumption on age about growth on the gradient, do you have
it's the same. Here I will mention it's the same as in the Laplacian when S goes to obtain this result by Quidner, Polacek, Quidner, and Supplé, which is I will mention because it's good to. Oh, sorry for that, but I don't have it in the other part. So it's just that where it is, it's at the beginning, so it's really there. That's the T can grow up to this number, which is exactly the exponent when S is 1, corresponding to the fractional. I mean, to the Laplacian case.
Quidner and Supplé use that assumption to get the control on that?
Yeah. No. I mean, that is used to make existence and have the control. So it's the same. It's exactly the same assumption. Somehow, for having this assumption, just one remark, to having this assumption is really that you need to go, you need to have to disestimate from 0 to right to S in all the range there. So that's, because for the Laplacian it goes to 1, but here to S. But this is the assumption on the gradient perturbation. And the other, of course, is subcritical in U. So yeah, here I wanted somehow to tell how can I prove this. So this estimate. It's relied on the scaling argument, but something called that the doubling lemma and so on. And here it's why I need somehow just I can have a super solution and just this restriction. I think it's not natural, but I can avoid it because somehow I don't have control. I will mention why this entry into the game. So what's the idea of the proof, which is more or less the same idea of the paper I'm talking with of Polacek, Whitner, and Souple, which is, as before, you say by a contradiction, you assume that there is a sequence of points having the bad behavior. So you take a sequence that have the wrong behavior. And then I will define this quantity, which is this right-hand side evaluated at any point. And then what's the doubling lemma says, which is more or less some very nice thing, which is not that hard to prove, which is in that paper of 2007, which says that if I have a sequence like this, I can have another sequence which is still bigger than this or equal, and with this behavior, and moreover, in a neighborhood of the points, I can control somehow all values by 2 times these values. So that's somehow the key point of doubling lemma. The doubling, I think, is because there's 2 there, but I'm not sure. Just the spirit. But here, the thing is that here I have many points where I have this control. I mean, in all this ball, I have this control. So now I will rescale with that. So I define this rescaling with this factor, which is the nk of these points. But the thing is, when I rescale it, I have the equation in the ball of radius k. So that's the point here. Since I have this, in all the neighborhood, I have the equation. I mean, I rescale it in this ball, but I have the equation also in this ball, and then somehow the estimate that I have to pass to the limit that I have, that's the point here. I have it in all ball. I have that this is bounded by 2 because I rescale it. So I rescale it, and then in all ball, I have the control. But the problem somehow is that I don't know nothing about vk outside this ball of radius k. I don't know even an L1 control or L infinity control. So that's the problem that I have. So I don't have any control. And then to pass to the limit in no local equation, if I don't have control outside, I can't pass to the limit. That's the bad thing of working with no local thing, because somehow I don't have control there, but what I do there, I just cut by 0, and I get a subsolution, and then since I have a U-Will type theorem for subsolution, I can make it. So I use the regularity plus a diagonal argument. This converts to something log, but really to pass to the limit to the equation, I need to cut. And here is the more or less explained. So I define the double V, extending Vk by 0 outside the ball. So this satisfies is a super solution of the equation, and I can pass limit, and I have at the limit, I take the limit, I have this equation, and then this contradicts the Gidas type result I mentioned before. And then, of course, as I mentioned, the existing result is more or less direct. You need to work a little bit, but still the degree argument is very adaptable to this situation. So once a priori bounds are established, so I can prove the 2 main theorems. And so I stop here. Thank you.
Thank you. Any questions? Anyone? No. So this